similar triangles. So far we've taken a look at the definition of similarity, how we can use ratios, proportions to help determine similarity or apply similarity to polygons, specifically to triangles. So here we kind of see how it affects the other segments within a triangle that might possibly occur, such as altitudes, medians, angle bisectors. So basically there were like 4 huge theorems that you would have had written out. I kind of condensed it down to just this little kind of chart or sentence structure, whatever you want to call it. Alright, basically it says this: if 2 triangles are similar, then each of the following are proportional to the measures of the corresponding sides. And while it might not make sense as you're writing it down, as I talk about it, I think as we go through the examples, it'll start to kind of clear up. So if the triangles are similar, whatever that scale factor is that we've talked about, which is just the ratio of corresponding sides, the perimeters will follow the same thing. Altitudes will follow the same scale factor. Medians, angle bisectors will all follow the same scale factor. So whatever the corresponding sides work out to be in terms of a ratio, these 4 things will work out to be the exact same thing as well. So take a second, copy those down if you haven't already. Alright, so just a couple of quick examples to kind of illustrate what all of this is saying. Example 1, you see we've got 2 triangles. You're told that triangle ABC is in fact similar to triangle DEF. Again, we've got a little symbol for similarity here. What is the perimeter of triangle DEF? Well, as you're drawing these out and copying them down, you'll see that triangle ABC has all 3 sides measured out, 5, 6, and 7. Triangle DEF, on the other hand, we only know one side length, that's 3. We don't know the length of EF, we don't know the length of segment DF. Could that be a problem? Sure, if you're trying to find perimeter, it's always going to be a problem because you need to know all 3 sides in order to be able to add them together. Now, what we could do is we could take the ratio of 5 to 3, because we can see here that AB should match up with DF as we see in our similarity statement. And we could take that ratio of 5 to 3, and then we could take each individual side and figure out the missing 2 measurements here. Once we figured both of those out, we could add them all up, and that would be the perimeter. But there's an easier and quicker way to go about it, thanks to this theorem. Again, the theorem tells us that, hey, if I know that I've got similar triangles, and I know that I've got a pair of corresponding sides that match up, so I've got my 5/3, then the perimeter of these 2 triangles should match accordingly. So here, if I find the perimeter, 5 plus 6 plus 7, that's going to equal 18. So 5 is to 3, as 18 is to the perimeter of my smaller triangle. A lot easier to work with. 1 proportion, 1 measurement, and you're done. So now we cross multiply. I've got 5p equals 3 times 18, that's 54, divide by 5, and I see that the perimeter is going to be 10.8. And so that's the perimeter of my smaller triangle. Does it tell me how big each of the 2 missing segments is? No. Does it tell me the perimeter of the smaller triangle? Yes. Is that what I wanted to find? Yes. So a little quicker method there in order to determine the perimeter. Again, all based on that ratio of the corresponding sides between the 2 triangles. So, and that again will hold true not only for perimeter, but for altitudes, for medians, and for angle bisectors, which we'll take a look at here in a minute. All right? Two more examples to take a look at. If you want to pause so that you can copy everything down, probably be a good idea to do that right now. Okay, so we've got 2 triangles here. Triangle RST and triangle MNP. Notice here we've got a segment going through each of our triangles. Here's segment SU, over here we've got segment NL. They're angle bisectors. How do I know that? that because I'm showing congruence between my angles here and here. As we did with the perimeters, the angle bisectors will be proportional to each other based on the corresponding sides. So, if I want to determine the length of segment MN is going to match up with segment RS. So I can sit here and say, alright, I'm going to take my 12 and compare that to X. That should be equal to the ratio of my angle bisectors. So here I would have 9, over here I would have 6. And now again I can cross multiply and divide. 9x equals 72, x equals 8. And so I know that that is the exact same thing as the length of segment MN. And that's it. In our last example here, we're going to take a look at how the altitudes fit into this. Notice that with the obtuse triangles, the altitude again will fall outside the triangle here. So that's what these little dashed lines are representing. Extension of the side, and then of course the altitude from, that vertex. So what is the length of the unknown altitude if the two triangles are similar? So again, it's already stated they're similar, which means you know that corresponding sides are going to be proportional. And again, you need to know that in order for this stuff to work. So I've already kind of pre-set up the proportion for you here. Altitude compared to altitude. Now, does it matter if I go 7 over x or x over 7? No, just make sure that the other ratio is set up consistently. So here I went 7 over x, so that means I'm going to go 8 over 10. Could I flip both of them? Sure. It'll still work the same way. So we cross multiply, we get 8x equals 70, divide by 8, and I know the measurement of this altitude, the one I was looking for, is roughly 8 3/4. So that does it for this set of notes. Again, last section of notes for the chapter. If you have any questions or if there's anything you might have missed, go back, take a look at it again. Further questions, bring them to class, and we'll talk about them when I see you. Bye.